This is 2427, suggested problem. This one says you have a thin spherical shell of charge of radius 14 centimeters. Let's see, so we can draw that. Remember, this is a three-dimensional shell. Well, we draw everything in two dimensions. Three-dimensional shell, 14 centimeters, and it has a total charge of 32 microcoulombs. It didn't say if it is an insulator or a conductor, so what that means is it shouldn't matter in the problem. So if it doesn't really tell you it's a conductor, you should never use this idea that the field is somewhere zero because it's inside of a conductor, because it's not in a conductor. It's just a thin shell of charge, so you can imagine that it's on an insulator. The question is, what is the electric field at 10 centimeters from the center and at 20 centimeters from the center? So what they're doing there is setting it up so that you are inside the shell at 10 centimeters. So there's 10 and then 4 more to the edge. And then, same question at 20 centimeters. And there you're outside the shell. So you're probably going to get different answers for the two. And they want it actually in terms of the actual electric field because they're giving you everything you need to know. They're giving you the total charge and they're giving you the distance. So we're going to solve this with Coulomb's law. So let's do part A at R equals 10 centimeters. You're inside the shell. So what we want to do is we want to use symmetry. We want to use, for a spherical system, we probably ought to use a spherical Gaussian surface. Right, so a spherical Gaussian. We want the field of 10 centimeters, so we should make a sphere with a radius of 10 centimeters. And we use symmetry. Symmetry will tell us two things. It'll tell us that the E field is always going to be out or in. The E field will always be along the radial direction, no matter where you go, because why would it be any other way? The thing is spherically symmetric, so the only direction in which things change is in the radial direction, so you can only have an E field in the radial direction. And the dA, the area vectors, so if this is A, and this is E, it would be like that, or dA. This is E, dA would be like that, same direction. So symmetry makes E and dA always the same, and symmetry makes E constant all the way around the sphere. So when we apply Gauss's law, we've used our two symmetry arguments to turn this into simply E times the area. They're the same direction, so E dot dA is E times dA. The E is constant, so it comes out of the integral, and it's just the E times the area. Right? So symmetry allows us to make it that simple. EA equals Q enclosed over epsilon naught. Alright, so the E field is constant at this position, so we just call it E. That's the E we're looking for. The area of this is 4 pi times the radius squared. So the radius is 0.1 meters squared. The Q enclosed is 3.2 times, I'm sorry, the Q enclosed is 0. And epsilon naught is epsilon naught. So since we have no charge enclosed, there's no charge inside, charge outside, doesn't matter, then of course E is just 0. Okay. So the E field inside this spherical shell of charge is 0. That's not because it's a metal. Okay? It has nothing to do with it being a metal, it has to do with symmetry. Whenever you have a spherically symmetric and evenly distributed sphere of charge, the E field inside will be 0. Nothing to do with being a metal. Okay, let's do part B. Part B is the same question out here, and R equals 20. So you do the same thing. You draw a Gaussian sphere, you use symmetry arguments to turn this into a simpler integral. So you say EA equals, again, Q enclosed over epsilon naught. And now, Q enclosed is what? It's 32 microcoulombs. It's spread evenly over the surface, but it's all enclosed. So it's equal to 32 times 10 to the minus 6 coulombs over epsilon naught. And EA, okay, well E is what we're looking for. E times 4 pi, and then 0.2 meters. 0.2 meters squared, 4 pi r squared, 32 times 10 to the minus 6 coulombs, 8.85 times 10 to the minus 12. So there's every number you need. You plug in for E, solve for E, and you should get 7.2 times 10 to the 6 liters per Coulomb. And if you want to make it a vector, you can, and just say it's in the radial direction, always pointing out. Okay, so inside it was 0, outside it was 7.2 million newtons per Coulomb.